Hi, hello. I'm Max, a tech artist from CDPR,
And I'm Hugh Bowles, and I work on the Procedural team as a senior tools programmer with a focus on runtime generation and GPU execution.
And here we are to talk mostly about PCG in Witcher 4 tech demo. Not about specifically the Foliage, but about its distribution in the world. As you see, it's pretty dense. At least in my opinion, looks pretty good. So I'll be talking mostly about the practical use of PCG, so how I used the system in the demo. And Hugh is going to expand a bit more on its technical side, on its performance, future, and stuff like this. A quick reminder what the Runtime PCG it is, because it will be very much relevant. It's just a trigger in the PCG, and it will signal the system when to update it. There are different triggers. Runtime specifically, of course, means it will be triggered in runtime. And it's almost always used with a partitioned setting. What it means is that PCG will divide the world into this grid-like structure, and every cell will be updated when you get close to it, which is depicted on this image. Otherwise, it's just a normal PCG. A great benefit for this approach is that whenever you modify a parameter, rather in editor or in runtime, it doesn't matter, the things will be updated immediately, which is very important for artistic work. Another important thing we wanted for the Witcher 4 tech demo is for this runtime PCG to be executed on GPU. Because as you'll see later, I'm mostly using it for Grass. And Grass is mostly a visual component of the picture. And you don't want really visual components to fight for performance with gameplay-related tasks. Luckily, PCG team just released the GPU support, which is not really a mode per se, but just a set of nodes. Some of them are just a checkbox, as you see in the picture. You click it, the node works just the same, but on GPU. But there are some GPU-specific nodes which are especially powerful. That's what you see on this picture. They are categorized as custom HLSL. And they are especially great because they are essentially a blank canvas. You can write your own logic there. You can combine multiple logical steps even in the same node. There are different flavors for the node. And they mostly differ in how the node structure its works inside. So for example, point generator will generate certain amount of operations based on however many you say. Like on the interface of the node, you say like, yeah, make me 1,000 points. While point processor, you give it a set of points, and it will just look at this set and decide on the number of points how many iterations to do. For the node, you get this UI, which is 3 text panels. The first one is, well, I call it hints, but actually it's just declarations for functions. These functions are dynamic, so whenever you change inputs for the node, you'll get different kinds of functions. So it's very handy. The middle panel is for your own functions. It's for code optimization and code organization. And final small panel here is for your own logic. It's the main work area. In my case, you see it's just 5 lines to spawn the grid of trees on a landscape. So no boilerplate at all, which is, in my opinion, awesome. Now, where the PCG runtime sits, or like PCG in general sits in the Foliage pipeline for the demo, we identified multiple criteria, and one of them is asset importance. So the big assets, hero assets, stuff like this, they will be placed almost guaranteed by artists. And so it's not really PCG at all. And that's what you see on this picture. It's purely hand-placed assets. Next, we give our artist a tool, PCG-based one, to fill areas with like generic foliage, let's say. The tool is for medium-size assets, like from shrub to a tree. The logic for placing there is kind of not as complex as hero assets, of course, but also not as simple as just randomly placing stuff, which means that we can potentially come up with a BCG graph, but this graph is not runtime. It will be pre-baked foliage. And finally, to finish the picture, we need some grass. Although it doesn't seem like it, there are more grass instances here than all other foliage combined, which means we cannot, unlike a previous slide, we cannot bake this foliage. We have to generate it in runtime, because otherwise we'll run into the performance issues. Another big criteria is area importance. So not only asset is important, but where it is placed. So if it's some edge of the map or some area that nobody cares about, more likely than not, the PCG or like any procedural generation will be used to place stuff there. While for quest areas and like key visual areas, almost guaranteed it will be mostly filled by artists by hand. And anything in between, well, you decide. That's how I imagine this distribution in my mind. And that's how it works out in the demo. This is panel side by side. The first one is just hand-placed. Middle one is hand-placed plus pre-baked. And finally is the complete picture. Quick word about the tool we used for pre-baking stuff. This is a task system we made that collects data from different sources, from Unreal World, from other applications, and it organizes it into PCG readable data. It's fully preset based, so only one person have to know how it works inside, and he will prepare all of the cool biomes, if you will. It works on tiles, which means artists will not clash together. There will not be checkout problems unless they work on one specific tile exactly. And the tool is optimized for mostly quality and flexibility rather than speed, which makes it, well, in my opinion, great for this medium-sized foliage. Now for the grass. The way it's made, it's not only partitioned runtime, it's also hierarchical. And it means that there is every cell will be subdivided into more cells. The benefit here is that we have the one huge cell over the whole world, depicted in blue here. And this one cell is essentially for stuff you want to happen only once. So like reading graph parameters, some organization stuff there. And I'm personally decide to dump all of the CPU work there. And then you pass all of this data that you collected on the big cell to smaller cells and do some other work. For example, this red cells depicted here, it's 128 meters per one cell. And there I'm doing some work that has high overhead, but has to happen at some point. And once I've collected all of this data, I will pass it to the smallest tiny cell. They're just 32 meters in size. And there will be a lot of them, of course, because of the size. And the final scatter will happen on them. This is the like logical overview of where data comes from to the graph. And I have two main sources. One is landscape, and one is graph parameters. For landscape, it's pretty easy. I'm getting the height map, of course, normals, and through material, I'm getting grass maps. For parameters, it's nothing too special. It's slightly more, but it's slightly more tricky. I have two arrays of assets. One is skeletal, one is static, and one structure which is a setting per one grass map. So there is a decent chunk of parameters. Yeah, and once all of this are passed into the graph, that's how the processes look like, the logical overview of it. You can notice that I'm using CPU almost exclusively on this unbounded grid because I'm trying to avoid the CPU as much as possible. And once the data is collected there, I'm dumping it into the GPU right away. You can notice that landscape and grass maps are read on the 128 meter grid, as I mentioned. The idea here is that, of course, you can read the landscape on the huge unbounded cell, but then you're getting the whole landscape at once, which has memory implications. While if you'll read them on the smallest cell, it's also possible, but then these operations have a noticeable overhead. So you'll get into a performance issues that way. And I'm doing the scatter on both of the grids, and you'll see why in a second. That's the whole graph. If you ever worked with PCG, you know it's a very tiny, small graph. And even then, this blue box, which is the most of the graph, is just reading the parameters. It can be collapsed into the smaller subgraphs or some sort of loop, but then it will be slightly harder to explain, but in production you probably will do it. Now I'll go through every part of this graph. I'll explain everything. So this part is nothing too special. It's just reading the inputs for a landscape and settings. As I mentioned, we have a structure of, for every grass map, I have some kind of a structure. And the settings is part of the structure. I'm keeping a close mind of the order of the settings because because I'm using the order as a key to link all of them. That's another part of the inputs. This one is for assets. There are two streams. One is for static, one is for skeletal. And it's necessary because, well, for static, let's say for rocks, you don't need skeletal, and vice versa for grass, you do need skeletal. Then I'm classifying what is going where, and also I'm adding a one placeholder item to this stream, just to make sure that data will not be collapsed. Because, well, as I mentioned, order is important in my graph. And if artist did not provide any assets, the data will go away. That's another part of the computation on the unbounded grid. Here I'm doing weight renormalization. Of course, it can be done later, for example, when I'm scattering. But since this operation is common for all tiles, it's better to do it only once on the input side rather than in the nodes. Like in custom HLSL nodes. So it's a tiny performance optimization, but just so you know. And finally, for inputs, you of course want for your artist to have some way to paint where stuff goes. Luckily, Unreal already have a system for it, which is this landscape grass system. I have almost complete setup for it, except I don't provide any assets to this landscape grass system. And that way, the generate grass map node can fetch the grass maps and create PCG textures for me to sample down the line. And finally, for nodes, I'm doing the point generation, of course. And you can notice that I have two exactly same setup. And that's for a reason. Initially, there was only one, this orange grid, which I kind of renamed to be a dense grass scattering. And what happens there is, of course, I'm just scattering some points. But if you see a great deal of transition between these points and nothing. So if it's dense grass and nothing, you'll see a huge jump. An artist constantly asked me to increase the radius, of course. So you can't really fight this transition by increasing the radius infinitely. Then you'll run into the number of instances issue. So the solution I used is I added another scattering pass with this medium on the medium grid, which I called sparse foliage. It's exactly the same setup, just fewer number of points, and to compensate for lack in density, I'm also scaling them up a bit. And also they are cooled away using minimum draw distance and maximum draw distance. So for the closed grid, there is no minimum draw distance. For the dense one, it just matches the previous one. Of course, the picture here is not to scale, just a note. The actual radius is 128 meters for the dense and 256 for sparse. There are, of course, drawbacks to this approach. If you zoom very closely, you'll see the transition between dense and sparse, because you'll see the scaling of the assets. And for transition from sparse to nothing, I'm recoloring assets to match the color of the ground at the very edge, so it kind of hides the assets themselves. But I cannot really recolor the shadows from the assets, so you'll see the black spotches disappear. But luckily, if you don't zoom that close as on the screenshots, you won't see any issues. There is another one related to performance that Hugh will show later. But if your performance fine, then all fine. And now for code in these custom HLSLs I showed a bit earlier. That's where another great chunk of graph is hiding. With these custom HLSLs, unlike Surface Sampler, you don't get automatically points already generated for you. You have to find out their position by yourself. The node comes with the grid function, and adding offset to the function is super easy. But also Unreal comes with its source codes open for you, which you can browse, and I found the Halton sequence there, which in my mind at least looks a bit more dense than grid offset. Not as dense as Poisson, like somewhere in between, but still very good. And next, we have to figure out which rough category of assets we want to scatter. In the setup I showed earlier, I had this grass maps generated. And here I'm just sampling these grass maps. It's essentially a texture at this point. And I'm figuring out which is their value, essentially. And I'm using this value as a bias in randomization. It means that if you have multiple layers overlapping, you'll get a still smooth transition between your grass layers, because adjacent items might get different layers just randomly selected. And other than that, I'm just figuring out what is the ID for the layer and using it as a key to select appropriate settings and asset array. And finally, we figured out what is the point position. We figured out a rough category of assets we want to scatter on this point. Now we just have to select an asset from this category. That's what happens here. The way I'm doing it, I have a noise flowing through world calculated just like you would do in any shader. And this noise doesn't have any particular meaning to it. It's just for artists to have this asset grouping. In the UI, as you can see, they have a range where they can decide on, for each asset on what range it should live. And this creates this more natural groupings of assets, as you see these blue boxes, for example. So in essence, what happens is that there are kind of like a fertility map, you might imagine. It looks a bit more natural than just randomly selecting assets. So you can imagine that all of this setup was pretty tricky on the early development of PCG. Luckily, I had Hugh helping me and a whole PCG team. So let's hear from him what other technical things there are.
Thank you, Maxim. No problem, Walter. Yeah, so as we started building the grass graph and putting PCG through its paces, we identified a few principles for authoring high-performance graphs that we want to share today. Firstly, we use hierarchical generation to reduce the frequency that work is done, as Maxim illustrated. Secondly, we use GPU nodes where possible, which are dispatched using compute shaders and run efficiently on GPU hardware. Thirdly, we minimize CPU to GPU data transfers, which are relatively expensive, and we'll examine this in more detail, using a simple example graph which scatters assets on a landscape and uses a custom HLSL node. Inspecting the graph, we notice the small yellow up and down arrows on the highlighted nodes, which are indicating GPU uploads and readbacks respectively, and thus highlighting potential performance issues. We'll look at each in turn, starting with the static mesh spawner. This is currently set to execute on CPU and will trigger an expensive download of the point data after the custom HLSL node executes. For this, the fix is simple. We have a GPU backend implemented for the static mesh spawner, and it can be enabled using the node setting below. The two GPU nodes will now execute together and pass the data directly without involving the CPU. We are continuously working to expand GPU support across our built-in nodes, so it's worth periodically checking each release. Now we turn our attention to the highlighted surface sampler node, which is running on the CPU before doing an expensive upload of data to the GPU. We don't yet have a GPU backend for the surface sampler, so the solution instead is to implement the sampling logic in a custom HLSL node, such as a point generator, similar to the approach covered by Maxim in the previous slides. Notice we now have an upload on the get landscape data node, which is uploading a patch of landscape heights within the generation area to the GPU. There are options to remove this upload, which we'll cover in the later slides. Next, let's look at the get texture data node, which is doing a readback of the texture data to the CPU so that it's available for other CPU nodes to use. In this graph, we don't require the texture data on the CPU, so we can disable the readback using the skip readback to CPU node setting. This setting also applies to other nodes that output textures, such as the generate grass maps node. That leaves the final upload, which occurs after this attribute is created. Obtaining attributes from the CPU is common, for example, for graph parameters, which are CPU by nature. Despite being a small amount of data, this upload will have a significant and measurable cost. A good solution for this, which Maxim also touched on, is to enable hierarchical generation in the graph settings and perform this upload once at the unbounded grid level, either using an empty attribute set processor node, which has been added for 5.7, or by using a custom kernel type to build the attribute set. Note that the uploaded data flows down the high-gen grids without repeated readbacks and re-uploads. The data is uploaded to the GPU just once and is cached there while the component is generated. In a similar vein, GPU data can also flow into and out of subgraphs without repeated readbacks. So these are also safe to use with all subgraph types supported. Either way, the final graph with all the optimizations we've just applied will execute much more efficiently than the one we started with. So revisiting the get landscape data node. Firstly, when running on GPU, we recommend enabling get height only and disabling get layer weights, which can save some setup time and resources on the CPU. The landscape layer weights are not directly accessible on the GPU and should be sampled via grass maps instead, as Maxim showed. Even with these settings, there is a game thread cost to uploading landscape heights to the GPU, which is around half a millisecond on base PS5 to generate a 32-meter grid cell. As an alternative, if a height runtime virtual texture is configured on the landscape components, the system can use this to obtain heights directly on the GPU. This is efficient, but comes with no guarantees of residency within the virtual texture, so it's possible to sample the heights before the virtual texture is sufficiently populated. To address this, we have a preload path that sends load requests to the virtual texture system, and we used an initial warm-up time delay to give the virtual textures time to populate, which got us over the line for the demo, but we aim to have a more robust solution for sampling virtual textures in the future. In the meantime, we have this new hot-off-the-press node that just landed in the 5.7 branch that can generate a height texture using the same underlying path as the grass map generation. It generates on the GPU, so it has low CPU overhead. It does not depend on virtual texture streaming, and it comes with low additional costs over just generating the grass maps. It currently generates a height texture only, so normals have to be computed manually. So now let's move on to CPU performance. For GPU PCG graphs, this is predominantly render setup and resource management. While shipping a demo, we reduced the average game thread time spent in PCG for this type of graph by almost 50%. We are focusing on this again for 5.7 and have so far reduced this a further 10%. The graph below shows a capture of the game thread time used by the PCG subsystem over a playthrough of the demo on base PS5. The CPU processes tasks for pending cells up to a prescribed per frame processing budget, and we set a base budget of 2 milliseconds. The busy parts of the graph, especially around the middle, are heavy sections of the demo where the camera is moving fast and triggering many cell generations. The 2 millisecond budget is relatively large, especially at 60 FPS, and we originally planned to reduce this, but there turned out to be ample CPU time available for most of the demo, albeit with a couple of exceptions we'll discuss in later slides. So we left it at this value to maximize the throughput of cell generation and therefore minimize something that we call generation latency, which is the time from when a cell is scheduled for generation to when generation is complete. If this time is too large for a given camera speed, the generation may lag behind and the instances will visibly pop in. This effect is illustrated further in this diagram. The camera at the center is moving forwards and the highlighted grid cell starts generating when it overlaps the generation radius in red. If the generation takes too long, the grid cell may overlap the primitive cull distance in white before generation, while generation is in progress, and the instances will visibly pop in when it completes. So there's a balancing act between the camera speed, generation radius, primitive cull distance, and the processing budget being the key factors. Also, a test or shipping build will generate substantially faster than a development build. So as you can imagine, it's a bit of a handful. But to help with balancing these, we added in-world debug draw to visualize the progress of the generation. The red wireframe sphere is the generation radius, and wireframe boxes with grid coordinate labels are drawn around grid cells while they are generating. This is a useful visualization to understand how the generation is progressing during playthroughs. We also often took video captures and stepped through the videos frame by frame to correlate PCG generation with any visible pops in the build. So, revisiting the processing budget. We have the ability to set the budget at runtime. So while the default budget was left at 2 milliseconds, we dynamically changed this budget in two key places. We reduced the budget to a minimal value when entering the village using a trigger volume. Here, the PCG system is dispatching one set of operations per frame on game thread and worker threads before yielding. Setting the budget this low increased generation latency significantly, but it was okay here due to the slower camera motion. The other key section was the marketplace sequence, during which we paused the system outright to minimize costs on the game thread. The camera motion is relatively contained in this sequence, and there were no issues, such as the range of the grass being visibly limited or other. Now to talk numbers. The game thread time spent in the PCG subsystem was 180 microseconds average over the whole run. Of this, 130 microseconds was fixed overhead arising from the runtime generation scheduler scanning grid cells for generation and cleanup. We aim to drive these costs down by our continuing push on optimization. Now moving on to GPU performance. The graph below shows the GPU time spent executing PCG work over a playthrough of the demo. The work is executed intermittently when cells generate. Note that this is unfiltered data with measurement noise, and we verified carefully that the spikes here are not indicating a larger PCG workload on those frames. The average cost over the whole run was minimal, but more relevant is the cost average for frames when PCG work was done, and this was around 71 microseconds. The instance counts per tiles are around 10 to 20,000, and the generation kernels did not come close to saturating the base PS5 GPU. And also, our theoretical occupancy for our kernels was almost 90%. So we posit that in the future, this workload could be moved off the GPU critical path entirely and moved onto async compute. For the memory side of things, the demo was well below the overall memory budget, and detailed memory analysis did not bubble up the priority list for 5.6. In particular, the PCG cache was left enabled for the demo, which would have accumulated some data over time. This has, however, become a big focus for 5.7. We now have the vast majority of PCG allocations tagged so that they're attributed properly in memory traces, which can generate detailed reports like the one shown. The core memory usage of PCG, excluding the data generated, typically takes low numbers of megabytes in our test graphs. In the next section, I want to mention some tools that aid in using PCG in production. Firstly, some high-level tools relevant to all disciplines. These two CVARs pause and unpause the runtime generation and trigger a refresh of nearby cells, so very useful for just general sanity checks and initial debugging. In 5.7, we added an inbuilt debug overlay that gives some insight into what the system is doing on each frame. And this CVAR enables a debug draw showing the generation radius and currently generating cells that we saw previously. Finally, for the virtual texture usage, we have CVARs to enable and disable the virtual texture path and to configure the warm-up time. For HLSL authors, besides the usual debug and inspection features you're used to in PCG working also for GPU nodes, we also have a shaded debug print, which will expose a function that can write an array of values, which will be printed to the log after execution. And in 5.7, we've added a debug feature that randomly initializes GPU memory buffers before execution, which helps to test that all data is properly written, and also to reproduce undefined behavior bugs, which can be hard to pin down, especially when uninitialized data is often zero by chance. Any data initialization issues or logic errors in kernels can seem to run fine on one device, but crash on others. So this tool is important for production stability, and we recommend running with these regularly. Now, for engineers or those familiar with debugging tools, starting with the CPU side, we've improved the break-in debugger node setting so that it also works for GPU nodes, and it triggers a breakpoint when the compute graph containing the GPU node executes. We also now scope this to the currently inspected grid cell to avoid a flood of breakpoints. And for those set up for GPU debugging, we have added the trigger render capture feature in 5.7, which will do a scoped capture of the dispatch for that kernel. And now for performance owners and optimization, we have additional CVARs, which I'll go through very quickly, but check the help text and documentation for more information. We have CVARs for the frame budgets. We have a CVAR that throttles the number of generating components, which limits how many are allowed to generate simultaneously. And we have a CVAR to configure a pool used to recycle partition actors. And related to runtime memory, PCG has a cache where the outputs of CPU nodes are stored to save re-evaluation, which can save compute time but increase memory. The cache can be configured using these CVARs, and we have a post-generation GC trigger, which can be set to trigger an incremental or full garbage collection after generation. Finally, for GPU profiling, this can be a challenge at the moment due to the PCG work being intermittent rather than running every frame. Sometimes this means refreshing generation and trying to trigger a capture on the right frame, which is not a great workflow. To streamline this a bit in 5.7, we added a feature to repeatedly dispatch a kernel instead of dispatching it only once so that a trace can be captured reliably. We hope to improve this situation going forwards, and I'll revisit this in the future work section. But I wanted to leave these steps here so they can be referred to later when the talk is uploaded. So that brings us to the end of the tools section and to the final forward-looking part of the presentation, starting with current challenges and improvement directions. Firstly, Maxim illustrated the double ring setup and some of the limitations of this approach. It would be valuable to find a new approach or some combination of existing approaches that can efficiently generate a long-range appearance that is faithful to the near-field instances. As a side note, Nanite Foliage was enabled on the grass instances in the demo, and it helped greatly, but individual instances ultimately do not scale to the far distance. Secondly, virtual textures are a powerful source of data, and it would be useful to have a way to query virtual texture residency and/or more gracefully deal with partial residency in runtime generation use cases. And finally, as we discussed earlier, generation latency can be a tricky topic. In the demo, we benefited from the camera motion being one long continuous path, whereas teleports will exacerbate these issues. We have a PCG gen source component which triggers generation at its location in the world and is designed to address this, but we haven't yet used it extensively in production. We anticipate continued effort in R&D going into minimizing the impact of generation latency. And now some additional future work directions. As mentioned previously, we will continue to push on optimization, including driving processing costs down on the CPU side, and also explore async compute for GPU work. One major component of the CPU cost is setting up actors and actor components. We will ship experimental support for spawning primitives via FastGeo components in 5.7, and we are aiming to build on that to add a mode that doesn't use actors for the generation grid at all. Besides that, we will continue to push on expanding functionality. In 5.7, we have a first version of support for override pins, including the point count on the point generator node, and we'll extend this over time. We are also exposing the basic compute types and classes for 5.7 to allow you to write your own GPU node backends. And we will also add support for GPU generation of instant skin meshes. Next, many of the supporting tools are in an early state for GPU, and we look forward to improving them over time. The profiling window in particular needs a big update to reflect GPU memory usage and GPU execution costs, and that's high on our list. And finally, we're excited for the PCG framework to transition to stable production-ready state for 5.7. That means we are committed to supporting our current feature set, not breaking existing projects, and we're going full steam ahead with PCG development. Within that, the PCG GPU feature is transitioning from experimental to beta as our focus shifts to stability, platform support, performance, as well as expanding GPU support to more nodes as mentioned. And before we wrap, we both wanted to give a huge shout out to just a subset of the many people that contributed to this work. And with that, I'll thank you very much and invite questions.